Okay, hi everyone. So welcome to this last session before lunch. So it's the third session, so I won't take you for very long. And today I'm going to be talking about how you can still do JIT spray attacks on Linux Berkeley packet filter. And this work has been done in collaboration with my colleague Filippo, who is sitting here. Filippo, you can wave to people. And then our supervisor, Professor Azakon. And you can see all our various affiliations and things in the slide. But what you're about to hear is that, so I'll give you a short overview for people who don't know what is Berkeley packet filter, what's doing inside of Linux kernel, what's the JIT, what is the purpose of a JIT compiler in the for the Berkeley packet filter. And then we will take a look on this original JIT spray attack, which was done back in 2012 by Kegan McAllister. It's very actually beautiful attack. It was done at the time, and it used a couple of interesting tricks. But as a result of that attack, and it allowed to do the JIT spray attack on the for the Linux kernel. As a result of this attack, there was countermeasures implemented, and we're going to take a look on them. And we will show how we can overcome these countermeasures done in the Linux kernel to actually pretty much achieve the same attack. So achieve full JIT spray on the modded 4.4 Linux kernel. And I'm going to show some short demo, and we'll talk about also modern implemented mitigations. And I would like to tell that this work has been done as part of the Linux kernel upstream self-hardening project. I don't know if you have heard about it, but I'll have a slide at the end to tell a bit more about it. So what is Linux Berkeley packet filter? So if you read this definition from Wikipedia, as from attacker point of view, you can see, okay, this is a kernel component, so it resides in Linux kernel, which allows a user space process to supply a program and get it executed in the kernel context, which is like pretty nice from the attacker point of view. So you kind of have this in-kernel virtual machine which can execute code for you, code you want. Well, not fully the code you want, but so where is the packet filter, is Berkeley packet filter used? So, well, obviously packet filtering. So this is how it originally was introduced. So we wanted to have a mechanism in a kernel to filter packages like for certain sockets for the user space, which we don't have to do context switch between user space and kernel. And because otherwise you'll have to take package, deliver it to user space, copy the data, say, okay, here's the package, user space process will take a look on it, and most of the packages it doesn't need, so it will discard and say, okay, not interested. So for this point, we wanted to have this filtering in place that you can supply a program to the kernel and say that I'm only interested for all the packages coming through this socket, I'm only interested in these particular ones. And for that one, it's really a virtual machine. So we have this BPF virtual machine. We have certain operations where when you write a program, there's certain operations which allow you can fetch data from a packet, obviously, to inspect some data. You can do some arithmetic operators. You can use the constants. You can say that, okay, if some of this data is bigger or equal, or I don't know, compared to this constant, so all kinds of things. So pretty powerful, I would say. And they did, of course, think about security there. So there is a component called BPF verifier in it, which will do sanity checks. So when you supply this program to a kernel and say, but here's a program I want to get executed for my socket, when the data comes, it will try to verify if the program is sane. So it will check for obvious things, lengths, correct headers, which you use correct language with BPF machine, kind of instruction language, and all these kind of things. So, and the next thing which exists also where it's a JIT compiler. So the purpose of a JIT compiler is when you think we're talking about packet filtering, so it has to be very fast when it works. I mean, it's not so important, obviously, for desktops and things like that, but if they are in the networking equipment, it has to happen fast. And in order to happen fast, you can't write the code in the, I don't know, in C or anything. So it has to be native assembly to really execute it fast. So at that point, we introduced back this just-in-time compiler, which when you supply this program in this BPF instruction, it will verify and everything, it will convert it to the native assembly. So if you're running an Intel processor, it's going to be x86 assembly. It's ARM. There are many architectures that JIT support for Berkeley package filter. And if you check it on your desktop, like Ubuntu or something, this JIT compiler is going to be turned off because you really don't do that much filtering. But it's going to be turned on by default on all the networking equipment because it's really important for them. So to summarize, like how this all works, there's a simple diagram. It's very simplified, but it gives like a good introduction. So you have a process which wants to have some filtering down on a socket. So it will create this BPF program. It will write it in this BPF instructions language. And it will create a socket where it wants this program to kind of a filtering to happen. It will attach this, there is C code to attach this program to the socket. And this, as a result of this code, this program will get copied to the kernel space, and it will first go through the verifier to do the checks. And if it doesn't pass the check, the program is discarded. User space gets an error saying didn't work. And when, but if everything works and verifier approves the program, when JIT compiler is enabled, it will go to JIT compiler, which will convert this program and produce the assembly version of the program. And this is what's going to be executed every time the data passes through the socket. So pretty simple, has been working for ages. So what was done, so what Kagan did in 2012 is that he said that, okay, so he wanted to do this JIT spray attack. And he noticed that when I introduced you what kind of things you can do with the, in the BPF program, you can you can supply constants to the, say, for example, for comparison. So you can load the constants in this machine instructions. And you can actually supply payload instructions using these constants. This is what the key thing of that attack was. He used a number of different tricks to get it working. Like he needed to create, obviously for JIT spray to happen, you need to create a lot of sockets. And since the limitation is that each socket can only have one filter attached. So in order to spray your space with the many filters, you need to create many sockets. There is a limit in Linux kernel for how many sockets you can create. And he used this FD passing trick, which is like really nice trick to actually overcome this limitation and get enough sockets, actually 8,000 sockets. He used that number. There's no hard limit, you can do even more before you run out of memory. So, but he used 8,000 filters, 8,000 sockets. And I also have to refer you to our white paper. So I don't have time to go, it's half an hour talk, so I don't have time to go through details, but we explain these details in white paper and give proper references, so you can pick it up from there. But using this 8,000 filters, 8,000 sockets, he sprayed the memory where these filters are loaded, and kind of how he tried to make it was very simple. So he randomly guessed a page from this like way he was expecting filter to be, and then he just tried to execute in the beginning of the page. And this is proof of concept attack, so it doesn't in order to have real attack, you will need to exploit some kernel vulnerability and get a jump to the exact location you think your filter is, or like you hope your filter is, and you do JIT spraying. But so for this purpose, he didn't have any vulnerability. He just supplied his own kernel module, which just only its dummy kernel module just jump where it says to. So just to make sure like this is not really, because it's easy to demonstrate with JIT sprays, not to demonstrate a kernel vulnerability, which unfortunately happen all the time. So in order to show this the main part, as I said, is how you're passing payload using these constants. So you see here on the left, you have a pseudocode. So you as a developer, you can just define this constants. You can say, but I want my constant, you have this 5 byte you have 5 bytes for constant, you can define this constant to be this way. And when the thing is that when you pass this constant to the JIT compiler, it's just gonna say, okay, I have to store this constant somewhere, so I'm gonna just move it to the AX. So this is one of the default registers. So, and it's gonna generate this assembly instruction, is move this constant to EAX and move another constant to AX. And this is the code which is gonna be actually, and I mean, it's a normal code, nothing is wrong with it, it's not malicious. But there is this thing, especially, which is very useful in x86, it's called underline execution. So it's, you can, because historically x86 started from very small instructions. They even still support like this 1 byte instructions, like NOPs and things like that, and some other interesting instructions. But they support anything between 1 byte to 15 bytes. So the instruction can be any size. So it means that they have to support underline instructions. So you can start actually execution in any byte. And if you see here in the example from the right, if you move the execution of instructions just by 1 byte, you get pretty different outcome. So you actually have 3 bytes of instruction, which was supplied for your payload, which you can execute, and you can freely choose. And when you have these 2 instructions, this A8, B8 there, which the B8 comes from this move,
So you can't control that if you wanted to put an age. We defined ourselves here, but it becomes just a simple test. So it's a safe instruction you can walk over and you can get your payload. So you can have payload instruction with test instruction, payload instruction, test instruction, and you can keep going and then building your payload. So this is what was done in the past. So, and he got really great attack results and things like that. So of course, community had to respond in back and past, and it was two different responses. So there's some of you might know this JIT security, which is known upstream kernel hardening mechanism. They have like many good different protections, but as a result of this attack, they also released their own protection to it. So and it was just saying that okay, you can pass this payload instruction as constant. So let's just blind this constant. Let's just XOR it with some random garbage we generate random number to make sure you don't have this payload instructions in clear in your memory, so you can't execute. Upstream kernel went a bit different way. So I said that, okay, this is kind of, this is rather complicated, not complicated, but it's, they implemented pretty fast fix, which was, so the previous talk when we looked here, so it succeeded well because filter was always loaded in the beginning of a page. So it was just the way we did in the beginning. So what we did now, we said that, okay, let's not load filter in the beginning of a page. Let's choose a random offset within the page where filter is going to be loaded. So, and it's really chosen at the moment where memory is allocated in the kernel. And let's fill everything outside of that filter. Let's fill with this, what it's called legal instructions, architecture-specific legal instructions. In case of x86, it's actually a very legal instruction. It's 1 byte int3 instruction, which is used for this debug trapping. So when you debug a program or stuff, you can get this interrupt. So and we did it this way. So now it's actually much harder to do with I mean, it's pretty hard to guess where your filter is, because you have to not just guess a random page where a filter is located, but you'll have to guess an offset. And if you guess wrongly, you're going to be punished, because what happens when you execute in x86 case, when you execute in free out of kernel context, so you get this interruption in free saying, okay, if it's in user space, if the program is not ready to be, if there's no debugger attached, nothing, the program will just get killed and can continue. But in kernel case, it's getting this interruption and thinking, okay, I'm not debugging anything. It just results in kernel panic. So it means that like if you guess wrongly, the kernel will panic and your game is over. In the sense that, of course, the machine will reboot and you can start guessing again. But I mean, you can't. It's not very useful way of doing it. And upstream thought that this is enough in a sense that, I mean, it's a good protection that you couldn't get the previous attack working, and you have a fair amount of guessing and everything to do. And yeah, and this is what was done. So when we started to work on our attack, it not just we wanted to make an attack, we worked partly with the, so we worked within the self protection project. We worked together with actually one of the BPF maintainer who was working on developing the similar solution based on this JIT security idea, solution on blinding and constant. But we wanted to make sure, I don't know if any one of you tried to get any security features in upstream Linux kernel. Usually when you try to kind of do anything of that, you have to show this through case. So if you just say that, okay, here is this theoretical possibility of attack, we will kick you out and say that go away with your code. But if you show that the attack is real, then the talk is going to be different. So this was the point of our developing our talks. We wanted to show that this is actually still real. So we still need a better protection. And that helped greatly to make sure that we get the patches when they need it. So when I started to think, okay, how we get target now, since we know filter is random and everything is like in free. So we thought that, okay, our first approach was, let's just grow a filter, because there is a limit on how much the filter this program can be, but it can easily grow like over one page. And when it grows over one page, you can see like we simplified where. So you have the filter starting in the beginning of the pages. I mean, if you grow, for example, just if you take a filter program which is less than 2 pages, when you have a filter at least in half of the cases, it's from beginning. And like if you payload and like alignments and knobs and stuff, you can play with your payload and get like better or worse results, but you can pretty safely execute from beginning of a page now. So this is what we tried first. So we guessed a random page similarly, but trying to execute some offsets in the beginning. You can find details, and it started to actually work. So this way you can actually get it working. And unfortunately, this success rate is not very high here because, I mean, you still have these half cases when you jump to within 3 and then things go badly. So it wasn't working as good as like you would like it to work. Our second approach is totally different, and this is what got us the best results. So when I started to look how the filter is actually, how the memory is allocated for this filter, I don't know why, but it was done in a way that it will kind of, and we have a code in the paper and stuff, you can take a look. So how it will allocate it will, if the filter size is quite close to the page size, it wants to save memory. It doesn't want to waste the kernel memory. Kernel memory is kind of not memory to be wasted. So it would not, it will try to allocate this filter in a way that it will only prefix with 128 random bytes in the beginning at most. Of course, it's still random, so it's 0 to 128. So if you allocate your filter, the size of this page size minus 180 minus 4, this is just the fourth header, one of the header structure. So you can force the filter to be under one page, and you force your size of your int hole, so this random hole, to be maximum of 132 bytes. It's from 0 to 132 bytes, but if you know the maximum, you can easily jump over. And this is what we did. So we just made our filter of this size. We filled actually whole filter with just nopes to make sure like you don't have to, I mean, you have, when you jump, you pretty much always jump at the right place and you can execute well. And the jump is still the same thing. We have 8,000 filters. You jump, guess a random page, you jump, and you jump over the now maximum amount always. And you always safely land in the payload. And this works extremely well. And now maybe I can try to demonstrate this. Let's see. I'll just bring the, I have the VM running here, so this is just normal. Sorry, I can't see well from here, so I have to come here. So this is just normal Ubuntu virtual machine. So we are normal user here. So whatever, so I'm Elena, and we have our program here, just very simple. So we're gonna do one pre-step, which is needed. I'll explain what's happening there. So as you can see, well, so I mentioned the original attack because it's proof of concept attack. So we're not actually using any exploit here. So to find the vulnerability, so we need to still load our kernel module, which is the only thing it does is just jump to the place we asked it to jump, and it can't do any inspection. It's really trying to simulate vulnerability. And then another thing we do is that we enable the JIT. So this BPF JIT enable is just enables the JIT compiler, because as I said, in typical Ubuntu, it's disabled. It's going to be enabled to networking equipment. And the last thing we do, this is a bit of cheating. We kind of enable this keep, I don't know if many of you know, but this keep BTO restrict is used in kernel to hide the location of kernel symbols. But we do it the easy way here in a sense that we just when it works like on runtime, but you can do a number of things to not to do this. So first of all, this in times when we were doing this, which was beginning of this year, you can still just, these addresses, we don't change between the VMs. So if you're running a typical VM, typical kernel version and stuff, you can just pre-hard code, you can query a version, you can pre-hard code with numbers. And when, for example, this year at Black Hat USA, they have shown how you can even just by various leaks which exist, how you can just easily get location of the same kernel symbol. So there is a way, and people know how to overcome this. We do this cheating because it's not so important for this attack. We just want to show that JIT spray works. But this is the preparation for it. So after the done preparation, I don't know if I have compiled. I think it's, yes, it's compiled. So we just start a program. It's going to create a socket. So and it's getting it. You can see it's getting it pretty fast. So you can see that we now normal root, and and I can actually, because it's done in a way that I can, after I close the shell here, it will kind of restart the whole thing from the beginning. So and I can do it actually many times. It's just like it eventually hangs, because there is still a way. I mean, you can still jump to the even though we make sure that we jump over the entry section, you can still jump to a page. We just have our filter allocated tool, and I mean, there's some random unallocated garbage, and but I mean, you can just mess up with registers and things, execute something which is valid instruction. If it's actually invalid instruction, then you're quite okay because it can survive it. But if it's invalid, if it's valid instruction but messes up with some registers, then you might not get it. So I can still keep doing this. I mean, it will eventually hang, but just to show that, like, so you can say that the probability of this attack is 100%, like almost. So what you can, after running this for a while, you will get it pretty fast. And it really goes through the whole memory space, this kernel modular memory mapping space where the filters are located, and it just tries to guess a random jump, and it's pretty far. So now maybe since I have only 10 minutes left, I will go back to finish the slides to show the countermeasures. So let's see how much. So the mitigation. So of course, as I said, so we worked in collaboration with one of the BPF maintainer, Daniel Berkman. He has been actually extremely useful, and we had really great discussions about how the filter works, how the Berkeley packet filter works, and how kind of to understand inside, because it's not so. I mean, all kernel components are not easy, but this one is not particularly easy to get accustomed if you're new. And this upstream kernel commit is something which was, it's just one of them. There's a series of commits which were done, which make sure that now blinding is done, so you can't pass any more the payload using the constants, and it's pretty safe now for JIT compiler. So it was merged, if I remember right, in 4.7. So if you're using any networking equipment with JIT, so you want to make sure that you upgrade your kernel, you backport, whatever, but because this is really important, because you can see that, and where actually all our code is released, so we have repository and links at the end, so you can see our code, and anyone can do this, unfortunately, given that we find the vulnerability, the exploitable vulnerability to do the jump in a kernel, but unfortunately, this is pretty much coming every year, and not even one of them. But another just nice fix was done also in the beginning of this year. I mentioned this trick which you can pass as file descriptors to kind of overcome the limit, so which is now fixed also. So there's also one of the commits link there. It doesn't fully mitigate it because we tried it on the kernel which has this fix, and you can only go up to 700 something 25 sockets. But it's actually pretty enough for approach 2 to succeed as well. So it's you don't need that many even. So, but it's just nice things that it got fixed. And of course, there is more kernel address space randomization coming, which is some of us was already in 4.8 and work is going, and it's going to help greatly. And I wanted to mention this kernel self-protection project, which we are working on. This work has mailing list wiki, you can go check, and it's pretty nice because, I mean, many people like here and other security conference, they talk about vulnerabilities, which, I mean, they say, okay, we found this vulnerability, and when it got fixed, and when it slowly got fixed somewhere else, but they're going to come anyway. So instead of just trying to fix vulnerabilities, we're trying to think of the measures which will prevent certain classes of exploits from ever succeeding. And that's very important. Or when there are some other researchers who are trying to say, okay, we thought of this kind of, we wrote research paper, white paper, have proof of concept of this particular hardening mechanism, but it never gets to upstream kernel. So, and this is a place where you can show up and discuss the ideas and show the code and show, and if you're interested in writing only exploits, for example, you can contribute where exploits are also needed. So I really encourage you to check the mailing list, and it's happening right now, and there are plenty of interesting projects there. So that's about all for today. So again, white paper has much more. We have only 5 minutes left, so I think I'm pretty on time. So I can take questions now for any. I hope I explained it like simply enough that it's even if you never heard about this component, that you can get a high level understanding. And if you want more details, you can get it from the paper or from the links I have, and the code is in GitHub. So yeah. So if there are no more questions, thank you. 10 minutes.